All right, everyone, it is our last week, and I probably have sent you a final exam now, which I guess we'll make that due in 2 weeks. I hope it's been fun. Please remember to turn in your course evaluations. They look bad if you don't. It looks like I asked you not to, something like that, so please do that. Let's see, I don't have, there's just not much to say, right? It's just one more week. This week we are covering angular momentum. This is very unpleasant. This is why I waited till the last moment to do this, because it's relatively difficult, but hopefully if I've got my act together, I'm hoping that I've organized this in a way that it's understandable. We'll just do our best, right? Okay. Now, long-term goal of this is, if you really understand your angular momentum, what you can do is you can calculate term symbols. So that's what I'm going to try to do. I'm going to try to get us to be able to calculate a term symbol. And for like nitrogen, that's actually on your exam. You have to calculate the potential term symbols for nitrogen atoms. If you can do that, you really understand angular momentum. So that's the idea. All right. That will be on Friday. I have to build up to that. So how do we build up that? So again, the subject, the last subject, angular momentum. Mostly adding angular momentum. The spin angular momentum, that up-down thing that electrons do that we don't even really know what it is, plus their SPD type of momentum. Anyway, I'm getting ahead of myself. Now remember, we've actually been covering angular momentum in multiple ways for quite some time. There was the Stern-Gerlach experiment, where you get a magnet, one of them has a point. That's to make an asymmetric magnetic field. And you recall that we let's just shoot an electron through. I think technically we use silver atoms. And what you get is that the electrons are deflected either up or down. And if you histogram that, what you get is up and down. Okay, cool. So this is quantum mechanical versus classical. What we should have gotten is just blob, right? Okay, now by classical I mean the electron is a little magnet, so it can be pointed up or down, but it could also be pointed to the side, right? And if it's pointed to the side, it would just shoot through, and on average, you would be pointed 90 degrees. Up and down are very specific directions after all. Okay, but we don't get this, we get this. Okay, now from here, we derived all of those spin operators and wave functions. Well, we never really had a wave function. We just called it plus and minus, right? And we know that SZ operating on plus and minus gives plus or minus h bar, plus or minus. And we actually define the states that way. Here's a little fun fact. These are spins. This is electron spin. We don't actually have a wave function for it. We just have alpha, beta, plus or minus, because we don't really know what it is. Anyway, I thought that was kind of neat. Okay, now, of course, that means that the spin matrix. I hope you can just do this in your sleep. If you're not, you're comfortable with this. So that's the SC matrix. Now, remember that this is the Hamiltonian if I'm talking about a Z Stern-Gerlach. So if the magnets are up and down, then basically the Hamiltonian is just SC times a constant, which we covered before. And that's why the basis set is diagonal. Remember that when you have an operator and you have a diagonal representation in a certain basis, if it's diagonal, then those basis functions are the eigenstates of that operator. And again, we'll say that this is like the Hamiltonian if the Hamiltonian is the magnetic field in the z direction. All right. Now Sx, of course, let me just do that in matrix form because it's a little bit easier for me at this point, in all honesty. 1, 0, 1, 1, 0. And therefore, the Sx plus or minus state is, what I'm having to do here is I'm having to make a a linear combination of the SZ basis states because the matrix is not diagonal, right? This is by definition not diagonal. So because of that, and remember, it's not diagonal in the SZ basis, plus or minus. So those belong to SZ, they don't belong to SX or SY. So neither are diagonal, and so their eigenstates. So by the diagonalization procedure, which you've seen many, many times at this point, gives you what those states are. Oh, there we go. Hopefully I didn't mess that up. Okay, again, it's really important to remember this. Remember this. These matrices are not diagonal. This is the representation, the plus-minus basis set. They're not diagonal. They have to be diagonalized to get the eigenstates. Because if I just take SY and I plug plus on it, I get junk. Because I will not get the plus ket back out on the right side. Remember, on the left side, operator ket, I need to get an eigenfunction times the same ket, and SX and SY don't do that with plus or minus. Okay. Now recall that we also covered this. By the way, this is not a review session, although it seems this way. Z, X, Y. So if you go right, this is like a forward cyclic permutation. If you were to go backward, SY, SX, you get IH bar, you get minus IH bar, whichever one you're missing, which is SZ. And we covered that before as well. On and on and on and on. Okay, so also SZ, SY. So basically I've done them all now, right? That's I, H bar, SX. That one's technically a forward. Is that? No, is that right? No, hold on. ZXY, no, XYZ, ZXY, ZY. No, that's backwards. So that's minus. Yeah, that's minus. Okay. Now, remember that I blabbed on and on about the need to diagonalize these matrices. The reason I had to do that is right here. These tell me the same thing. These tell me that the SZ states are not going to be okay with SX or SY because they commute. Or they don't commute. They don't commute. They technically have a non-zero commutator. Because of that, the matrices were guaranteed to be not diagonal. And again, this is hideously important. Now, there were some other operators that some of you had done one of your homeworks on, although that's not what I wanted you to do, but you did it anyway, and I have actually talked about these before. The raising operator, so this is like the creation operator for the harmonic oscillator. We talked a lot about creation and just annihilation operators. Again, you will see those in talks all the time. Okay, there's an analogous operators for spin for the Stern-Gerlach field. There's the raising, here's the lowering operator, and for some reason, I don't know if it means anything, they're related to X and Y. And, okay, so this guy looks like this. I know there has to be an H bar because SX returns an H bar. H bar over 2, but then I'm adding the Y to it, so, and then this guy is just the other diagonal. Okay, so again, here are all the operators. Now I want to point out, the reason I'm bringing up S plus and S minus now is because of this. Let's see. Okay, now the S operator, just what's your spin, of course, is a vector sum of, oh, I'm writing too small, aren't I? For me, it's big. Sx, y, and z, just added together. Okay, so now again, the reason that this is a vector is that s squared is then sx squared plus sy squared. So you don't have any cross terms. Okay, now remember that it's kind of important to keep s separated in your mind from s squared. You know that cosine is an eigenfunction of p squared, right? Double derivative of cosine is basically cosine. But cosine is not an eigenfunction of p itself, just the derivative. Derivative of cosine is minus sine. So that is not an eigenfunction of momentum, but it is a momentum squared. So there are good reasons to believe that these are actually kind of different, nutty as that is. Okay, so let me show you something about s plus and s minus. I know this is a potpourri of operators, but anyway, sx plus I, sy. I'm going to forget the hats, but I don't want to deprive it. Anyway, and always keep track of what's in front of what, just using your FOIL rules that you learned in middle school, but make sure you don't screw it up, right? Okay, sx squared plus sy squared. I'm going to read this, make sure I don't screw up. Then you get plus I sy sx minus, yeah, there's going to be a minus sign, minus sx sy, which we immediately recognize that this thing is, of course, the commutator sy sx, which is fortunately, of course, let's see, that's going backward, right? So that is minus I h bar sz. Okay, so now what? So this is actually equal to, okay, so I'm going to do something really, really kind of funny here. Okay, what I'm going to do is I'm going to say sx squared plus sy squared. Now watch out for this. I'm going to add sz squared. Now remember, there's not been an sz yet, but I'm adding it. Now I'm going to subtract it. And proofs, like the book does this, and you're like, it comes out of nowhere because you don't realize that that's what they're doing. Okay. And then you add in HSZ. And let's see, okay, that's plus, minus I squared, which is plus. Okay, HSC. Okay, so that works. Oh my God, this is crazy, isn't it? Okay, so this ends up being S squared minus SZ squared plus H bar SZ. Okay. This is awful of me, isn't it? Okay, let me do the worst board you've ever seen me work before. Okay, so now S squared is now S plus S minus minus SZ squared minus H bar SZ. Okay. Now, why did I do that? Right? Why not have a simple expression here, only to, well, it's still kind of simple-ish. It doesn't look like I've really gained or lost, but I have. Now, here's what I've gained. All right, now, previously, the problem here is that the states of Sx, plus and minus, are not good with x and y. Okay, but these things, now I've got the SC, so I know plus and minus work on this. Now, they're not okay with plus or minus, but I know how they work real easy. If I'm operating on S plus S minus on the minus state, then that's 0, because S minus, the lowering operator on the minus state, just goes nowhere, right? That's 0. So if I operate on the plus state, then the plus goes to minus, and then it goes back to plus. Anyway, my point being that this is actually really easy to evaluate in the plus minus SZ basis set, whereas before, it was utterly going to suck. Right? Now, the whole point of raising and lowering operators is that you can see what couples to what, like in a matrix, like do you have a zero based on what's on top, your row versus your column? You can see what couples to what's zero and what's not, real easy. So that's why we do it this way. Okay, so with that, you can figure out, I actually had this in my notes. I was going to show you s squared on plus or minus. They end up being the exact same thing. It actually takes a while. So while I had written a whole page of notes to work this for plus ket, plus bra, and minus, it actually really did take a while. But anyway, it ends up just being 3/4 h bar squared. So s squared in matrix form, h bar squared 3/4, 0, 0, 3/4. Okay, so relatively simple matrix. You can read off the eigenvalues real easy because again it's diagonal. So you see that I've got the matrix is diagonal in the plus or minus basis set, which was really easy to calculate and see with that, even though it kind of actually wasn't. Okay, now here's the point of all this. God, this is hideous, isn't it? Here's the point. There are some things you can know with the plus or minus basis set, right? We have been working with plus or minus basis for a long time. I'm going to keep using that, right? But there's some things I can know and some things I can't know. I can clearly know SV. That's up there. Anyway, I can clearly know SC. That's what it was designed for. So that's a no-brainer. I can calculate s squared. So it's good with s squared. And yeah, anyway. Is that it? Damn. So the point being is that this basis set is amenable for giving me SV, s squared, but not sx or sy. That it will not do. And I need to know that. Now the ultimate reason is, by the way, is that remember that the long-term goal here is to come up with term symbols, which means I have to start adding angular momentum together, and spin is a type of angular momentum. The problem with adding vectors is when you don't know what the vector fully is, right? If I'm going to add two vectors in 3 dimensions, I have to know the x, y, and z component. But with spin, or any other type of angular momentum, you never have all the information because of uncertainty principles. So you can imagine it's really hard to add the angular momentum vectors when you don't have the entire vector information data set because of uncertainty. So that's point 1. Point 2, remember that spin is a type of angular momentum. So the other type of angular momentum, which I'm going to review right now, is the L type, a electrons on a string and I'm twirling it. SPD states, that stuff, you know that. Those have L operators, which all I have to do is change this S to an L, and everything is exactly the same. Now your book goes to great lengths to try to prove all that. Given the length of time we have, which is no time, and the fact that it sucks, I'm not going to do it. Just want to point out that just change every S you see here for an L, and you have got the L-type angular momentum operators. They have the same uncertainty principle. The part that gets a little bit funkier, though, is that you don't have plus or minus half. It's either going to be 0 for S, 1, 1, 0, minus 1, those are P's, minus 2, minus 1, 0, 1, 2, those are the D's, and we're not going to go past D. So again, the only difference is the operators are exactly the same. It's just you're not working on plus or minus. You're either working on 0 for S, 1, 0, minus 1 for P, or minus 2, minus 1, blah, 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 blah. Anyway, I already said that. Okay, now let's review L-type angular momentum. And to do that, I will clear the board. I'll stop the video for a minute to do that because the board is a mess. All right, everyone back. Okay, so L-type angular momentum. Okay, now remember, particle on a string. When you hopefully learned this as an undergrad, you had a particle on a string and you whizzed it around, right? You can turn the kinetic energy double derivative of x plus double derivative of y plus double derivative of z into the same with r, theta, and z. So this is just the kinetic energy. It's just more real. You know, we didn't have a definition of kinetic energy for plus or minus 1/2 spin because we don't even know what it is. We do have energy for a particle on a string that we're whizzing around. Of course, that's easy to know. It's actually r cross p. R cross p is how you derive all this, but whatever. Now, actually, you did a little bit of that on one of your homeworks. Regardless, if you have the Laplacian, whatever, del squared in x, y, and z, it's easy. But when you go to r, theta, and phi, it's a bit harder. And the parts that only have angles in them, those are the angular momentum parts, right? That makes sense. Okay, what were they? You may recall, we didn't actually derive this. You derived the cylindrical one, and I didn't make you do 3D because 3D is rather nightmarish. There's this thing called a Podolsky transform that can do r theta phi from x, y, and z real quick, but I didn't cover that because it's just not really necessary. You can do some neat tricks with the Podolsky transform beyond going from Cartesian to spherical, but we don't really run into them. Okay, so hopefully you remember this. Awful pain, right? One of the more difficult situations is the fact that I've got a theta and a phi together, which means that we have an issue with separability, but we can solve that. Of course, when we operate on the wave functions, we get h bar squared, L times L plus 1, over 2 m r squared, which is usually 2mi, where I is the moment of inertia. I'm not going to worry about that, it's a detail. Of course, times the wave function. Now, of course, what this is the L squared operator, L squared over 2i. This is what that operator is. So L squared doesn't return L squared, it returns L times L plus 1. It's almost L squared. Remember that when we did kinetic energy momentum, linear momentum, p squared over 2m, we got h bar squared k squared. When we did, anyway, there's other examples. So I'm looking for like an h bar squared L squared, but it's just not quite. It's h bar squared L squared plus L. Anyway, that's one of the weird differences. I don't know why that happens. Okay, so recall that the wave function is separable into phi and theta components, where you have, it's actually the spherical harmonics, which are labeled L and M goes from minus L plus 1, to plus L. So again, you know that, you know it intuitively. There's only one S state, there are 3 P states, minus 1, 0, 1, Px, Py, and Pz. There are 5 D states, because L is 2. 2 minus 1, 0, 0 plus 1 plus 2. So 5 D states. And again, you know this, and we're not going to go past D. Last thing I wanted to remind you, well, here, I'll remind you of this. This is a detail. Remember that the phi wave function is e to the I m phi, whatever. And the way that this is visualized is like this. You have a cone, and I'll explain all this in a second on x and y. So here's x, and here's y, here's z. Okay, now let's say that we're describing a finite L. So let's say that's L equals 1. So the vector's length along the side of the cone is L, and then the projection is MH. So the length is, of course, I want to say 1. It's L times L, sorry, what's wrong with me? It would be the square root of L times L plus 1, so H bar, and of course, right, I just took the square root of, this, and the height is M H bar. Of course, there's if this is L of 1, so let me draw I'll draw an L equals 1 state. So that means that I have to put 1 on bottom. So this is the MH plus 1, so this is MH, sorry, how do I do this? Plus MH, this is minus MH, obvious, right? Now recall so if I'm doing, so I'm doing a P state, there's also the M is 0. So there's 0h, angular momentum in the z direction. Now, let's see, two things about that is, you can see how important it is to know what M sub L is, right? It's called the magnetic quantum number, because you can see that this would like bend upward in a magnet, this would bend downward in a magnet, and that one wouldn't bend at all. So that's why it's called the magnetic quantum number. Since I've done a P state, we have plus 0 and minus 1. And the other reason that we do this with a cone is because, as I said, the L operators work just like the S operators. I can know what the angular momentum is, or angular momentum squared. I can know the z component, 1h, 0h, or minus h. I can know that, but I can't know x or y. So when I draw this as a cone, the projection onto the x-axis is never known. The x or y component, right? The x or y component, it has a component, I just don't know what it is, and the only way to draw that is as a circle in the xy plane. So I just want to remind you about how to read these things. Last one, in case you also forgot, when I draw a vector like this, remember that that's actually the axle of the wheel, so this particle is actually spinning like that. Right, so remember the angular momentum is the axis of a wheel. So anyway, that's what that actually represents. So sometimes people think that the object is actually spinning this way. It's actually not, it's actually that way. Anyway, just want to remind you. God, let's see, what else I want to say? Okay, so hopefully this is all just a big reminder. And the long-term goal is, let's do a 3D1. Let's talk about a hydrogen atom that happens to have an electron in a D state. And so there's 5 of them, 2, 1, 0, minus 1, 2. And let's say, you know what, I'll do 3D2. Let's make it interesting. Let's do that. How, if I am a PhD physical chemist, do I describe this configuration? You use a term symbol. How do you know what a term symbol is? Well, the term symbol represents all the angular momentum. All the angular momentum added. Now I have 2 electrons. I've got it plus 2, plus 1, 0, minus 1, minus 2. Okay, it's in a D state. I have 2 electrons. One is spin up, spin down. And they're both in the M sub L of plus 2 state. So you see I've got, okay, spin up, spin down, S type. So there's 2 angular momentums. I also know that they're in a D state, so now I know 3 things, and I know that they're both in the M sub L of plus 2. So I know 4 things about these 2 electrons. There's only one term symbol. So how do you put all that information in a term symbol? Well, there's a little bit more information in the term symbol than just one thing. Technically, the spin, this is obviously a singlet. Now, technically, it's in a D state, by the way. And we're going to cover how to know that. It's not hard to know that it's a singlet, but I can tell you that it's in a, actually I meant to, I screwed up. I meant to actually do, it's actually in an F state, by the way. That's an F state. I screwed up. I meant to keep it easy. Okay, so, the reason I screwed up is that that's actually a D state. What I did before is technically a singlet F, by the way. But anyway, let's keep it simple. Let's do a D. Sorry about that. Okay, now I can tell it's a singlet because the electrons are paired. But how do I know it's a D state? We're going to cover that. That's what we're going to be covering on Friday. But I can give you a little bit of a hint. Notice that P states, why is it a D angular momentum and not a P angular momentum when it's in a P orbital? right? Now think about this. P orbitals have m sub L of 1, 0, or minus 1. But this sucker has an m sub L of 2, because there's two that have plus 1 m sub L's of angular momentum. So the m sub L of this state is 2. A p orbital cannot have an m sub L of 2. It can only have an m sub L of 1. So therefore, there's no way that this is a p angular momentum state. It has to be a d. Because a d can have plus 2, plus 1, 0, minus 1, minus 2. D can have a plus 2 m sub L. So singlet because, well, it's paired, and D because there's no way that it can be a P. It has to be a D because the m sub L is 2. Anyway, so we're going to be covering all this stuff. I just wanted to point that out. Another reason to couple all the angular momentum is, so remember that the way to read this is 2s, you should, I hope you have seen this before. 2s plus 1, that is the singlet triplet stuff, so this is a singlet because the electrons are paired. L, we just talked about that, and then J. J is L plus S. So, and in this case, so therefore this is 1D, S is 0, L is 2, 1D2. That is a 1D2 state. Okay. Now, the reason I'm doing all this is because total energy is proportional to J squared, right? Not L or S, but the total angular momentum. Angular momentum squared over 2I is the angular energy contribution, right? So I need, it's great to know S and L. You do need to know them. But what you want is J. You have to get J. You don't have J, you don't have the energy. You don't have the energy states. Remember that states of the Hamiltonian, if the Hamiltonian has J squared, the states of the Hamiltonian are what we consider the real states. This is actually, this one works. This one works. This is actually a state of J. But let me show you one that's not. I'm going to do P's. Let's do this one. Again, plus 1, 0, this is the m sub L. Plus 1, 0, minus 1. I'm going to do this. Guess what? That is not a pure J state. This, if you operate on, J squared. If you operate on this sucker, if you operate on J squared with this wave function, you don't get the wave function coming back. It is not an eigenfunction. So, 2p plus 1 plus 2p minus 1 operate. What do you get? You don't get the wave function back. You don't know the energy, right? So this sucks. So, and by the way, the answer is that to be an eigenfunction of J squared, I'm jumping ahead, but I just want to show you. You add it or subtract the, right, so that's up, down, you add or subtract down, up. Then it happens to be an eigenfunction of J squared. And again, I'm just previewing, I just wanted you to see how this works. Okay, so now you see that we've got to get eigenfunctions of J squared. We have to. And it's going to be a little complex. Once we do that, we can get the energies. Now there's another thing, which is spin-orbit coupling. So, here, let me, before I go to another board, spin-orbit coupling. Okay, it's basically a constant, L dotted into S. Okay, spin-orbit coupling is a magnetic phenomenon. It's technically a relativistic phenomenon. You have to use, you cannot use the Schrodinger equation to determine that spin-orbit coupling exists. You have to use the Dirac equation, which is the relativistic form of the Schrodinger equation. We didn't get a chance to cover it, but anyway, the Schrodinger equation is not correct because it does not include relativity. The Dirac equation is correct, and it predicts spin-orbit coupling, but it is incredibly hard to use. So it's so bad we don't even talk about it in this class. Regardless, spin-orbit coupling has L dot S. Again, if you need to evaluate this sucker, you need to have the right energy eigenstates. And all this stuff are not eigenstates of L dot S. J states are eigenstates of L dot S. And I'll prove that in a little bit. Anyway, so and I just want to remind you a little bit about, we're going to talk a little bit more about spin-orbit coupling, because spin-orbit coupling is important for heavy atoms. How heavy? When you get about to the third row, you need to start thinking about it. In fourth, fifth row, it's on. Yeah, spin-orbit coupling is very strong. It's actually, spin-orbit coupling energy is more energy than the kinetic energies, than the angular energies of the electrons. So it's more important to think about the spin-orbit Hamiltonian than it is about the angular kinetic energy Hamiltonian, which is kind of nuts. And I don't think many people know good ways to think about that. Now, to remind you exactly what spin-orbit coupling looks like. So we have an electron spinning on its axis, and of course it's also in an orbit. Now that of course means that it is in it has to have a finite L. Electrons in S states don't spin. Despite their round representation, we know that the angular functions are just constants. They're just normalization constants. Once you get to P and D states, then the spherical harmonics are now cosine and sine and all that. Okay, so the problem is that I'll allow the electron to spin in the same direction. Remember, it's as though the electron itself is spinning. As though the electron is spinning on its own axis, which creates a magnetic field. That's not what's really happening. We don't really know what's happening, regardless. In this case, it's spinning whatever, this way counterclockwise, and this way it's spinning clockwise. So that spinning electric field, remember, the electron spinning on its axis, not that it's doing that, creates a magnetic field, but the way it spins around and around also creates a magnetic field. And the ways that these magnetic fields couple or don't couple creates energy. And again, for heavy atoms, it's more important than the actual rotational energy itself. Okay, so notice that I have drawn the electron up and down. Another funny thing is that actually, notice I've drawn the electron as alpha, as plus. I could have drawn the electron as beta or minus, right? I could have done that. And anyway, so you got to know a lot of stuff. You got to know whether the electron is up or down. Notice I kind of tricked you. I made this look a little easier than it is. The electron could be up or down, and it could be spinning with m sub L of +1 or m sub L of -1, right? That's what I also drew in terms of the L-type momentum. In either case, you see, I need to know SZ. I need to know SZ. I mean, this is clearly what's happening. And of course, I need to know SZ. Well, guess what? Watch this. Now, by the way, I'm still in big picture. I am just, here's the constants from the spin-orbit Hamiltonian. I'm still just motivating the need to do what I'm about to do, which is to figure out what the J states are. To get the J states, I'm going to make linear combinations of the, of the electron configurations like you learned in high school. So I need linear combinations of those. So those types of representations are actually basis states that need to be, I need to make linear combinations of those to figure out what the states are that are okay with J squared. Okay. All right, so now SZ and this term, those will wipe out. It's just, a thing with itself. All right, but then you see what I'm going to have a problem with? I'm going to have S, I'm going to have, oh my God. I'm going to have SZ and SX and SC and SY, commutators of SC and SX, SZ and SY. Those are not zero, so what you end up with is this. The LXs and LYs and LZs, those don't do anything because these are like in different dimensions. Your book mentions that these are different like tensors. It just means that you don't have to, it's like it's like they're not there, basically. You can just kind of forget that the L's, when you're doing an S commutator, you can just forget that the L's are there. You don't have to worry about commutation rules. You don't have to worry about them doing anything together at all. Okay, and as I'll show you here in a second, okay, this is the end. I can't do anything with this. And as I'm going to show you, this is actually the commutator of LZ with the spin orbit. And to prove that, I will do LZ in the spin orbit Hamiltonian. And, okay, what you're going to get is a constant. You know what this does is this also shows you that it is kind of important to recognize that when I made a lot of noise about being careful about moving operators around each other, you can't, you know, A, B, C is not B, A, C and all that. I made a lot of noise about that. In this case, you don't have to worry about that. The L's can just move right through the S's because they just don't exist in the same space. So that's fine. And that's why in this case I can know that this is, again, the SC just doesn't matter. You can just pretend it's not there. So I've got LZ and LZ, so this term is gone, but I'm going to have an LZ LX and an LZ LY minus LY LZ. Anyway, so I've got commutators. So I H bar LY S X. Right, LZ and X is LY. Just like we talked about a second ago. LZ and LY is going to be minus L minus LX. And again, the SY is there. It's like a constant, basically. And notice that this is just like minus SZ spin orbit. Okay, now the point of all this is when I drew this representation, I had to tell you what direction it was moving, so that's like L plus or minus. And I had to tell you whether it was spin up, that's SZ plus or minus. I have to know that because, I mean, I can see that one of these is not the same as the other. It has a different energy. However, that tool by which I calculate the energy, the spin orbit, sorry, that bothers me. Anyway, the spin orbit Hamiltonian, the thing I use to calculate the energy, will not work with the wave functions that I use to describe this because they commute. They don't commute. So when I try to write the wave functions for these things as I drew them, it's cool that I know what the wave functions are, but what's not cool is that when I operate them on the spin orbit Hamiltonian, the wave function doesn't come back, right? I don't get an eigenvalue equation, so I'm doing mathematical junk. The answer, again, is to form linear combinations of these states that are okay with the spin orbit Hamiltonian, that are okay with J squared. J squared and the spin orbit Hamiltonian are all, those have the same state, so they're cool with each other. But they're not okay with this. And so, of course, the way we're going to do that, just like I was reminding you before, is that we're going to form matrices, and then we're going to diagonalize them. And that's what we're going to be doing on Friday. So I have to see how am I doing on time. So let me wipe out the board, and let's see where we go from here. All right, everyone. So just wiped out the board. I see I only have a few minutes left. So let me show you where we're going with this. What you need to do is, well, let's see, let me remind you, what do I want to do here first? Okay, let me remind you of how L squared, this is kind of important, and I'll use Dirac notation. Okay, L squared on a state is h bar squared L times L plus 1. State LZ is, again, the px, py, pz part. The spin, which we don't think there's much to that, but we have to, unfortunately, it has to be added in. You know what? Put in a half, right? Put in a half. 3/2 times 1/2 is 3/4. 3/4 h bar squared. Remember we did that just a minute ago when we diagonalized the spin squared Hamiltonian? Totally worked, right? 3/4 h bar squared. Okay, then SC, which is alpha beta or plus minus, is of course, oh, you know what? I need to be careful, and I will be very careful. M sub L, M sub S h bar. You need to make sure that it's clear because those add up. This is all about adding angular momentum, and those add up in different ways. All right, now the goal is we can't work with this. It's cool that I know how to do this, right? We've gone over this and over this. This hopefully is like no problem. Spin up, spin down. L times L plus 1 is for P state, D state, Px, Py, Pz. None of that's hard. But guess what? None of it works with J squared. So what we need to do is this. We need to have a representation of J, and of course J being the total, J being the total angular momentum. J has to have its own M sub J, by the way. So if J is 1, then M sub J can be, I think technically it's actually 1 or 0. It has slightly different rules, but we'll cover that. Okay. Now, if I know 4 things, then you still know 4 things in a new representation. And so what you know is S, these aren't operators. That doesn't make sense like that. So you still know S, and you still know L. Okay, so my point here is that it's cool that I know this, but it's actually not useful. I need to know what J is, or J squared. And it's going to have an M sub J. You can't avoid, if you know that you have a angular momentum of P, an angular momentum of 1, you know that it has to have 3 states, plus 1, 0, and minus 1. So that's going to be true in J. Okay, and then we'll retain our knowledge of S and L. What this has to come from is this, for which we know L, M sub L, S, and M sub S. Now again, it's cool that we know intuitively how to draw like atomic configurations with spin up and spin down, Px, Py, Pz. We know how to make these states, right? It's no problem at all. And then, of course, the wave functions are like spherical harmonics, blah, blah, blah. But these aren't useful for anything. We have to transform that to that by diagonalizing that matrix. All right, so anyway, I've gone on a little too long. I'm going to set you up for what we're going to do on Wednesday. And then Friday, we're going to do a full-blown term evaluation. So I'll stop now. What we'll do next time is, instead of turning L and S, this is kind of a hard problem, like a p orbital, with 1 electron that spin up. How do we turn that into an eigenstate of J? Well, we won't do that one first. We'll actually do 2 electrons, each in an S state, so there's no L, but there are 2 S's. So we're going to couple the angular momentum of 2 spins. And what we're going to find are singlet and triplet wave functions, but we already know about that, right? That's why it's a good start. So that's what we're going to do first thing on Wednesday. All right, I think I've gone over time, so I'm going to wipe out the board and actually keep going, but you won't see me till Wednesday. I'll see you all then.